Welcome to this tutorial on interval estimation for the population mean when sigma is known. In the previous tutorial, we discussed how a point estimator from a sample can be used to estimate a population parameter. For example, the sample mean x bar is a point estimator for the population mean mu, and the sample proportion p bar is a point estimator for the population proportion p. In this tutorial, we will see how a point estimator, such as the sample mean x bar, can be used more realistically by adding and subtracting a value called a margin of error. This will give us something called an interval estimate. This interval estimate is a much more realistic predictor of where the true value of the population parameter is. So instead of using a single point, such as x bar, we compute an interval around that point, and the formula looks something like this. X bar, the point estimate, plus and minus some margin of error. For the interval estimate of the population proportion, we will use p bar plus or minus some margin of error. Now, in order to calculate an interval around the population mean, we will need to use either sigma, the population standard deviation, or S, the sample standard deviation, to compute the margin of error. In most cases, the population standard deviation sigma is unknown, and we need to use S, the sample standard deviation, to compute the margin of error. But there are times when we have historical data that can be relied upon to determine the population standard deviation, or a production process where the standard deviation is known. These types of situations, where the population standard deviation is known, are called sigma known cases. Let's look at the case of a light bulb factory that selects a simple random sample of 50 light bulbs each week to measure how many hours they burn. Each week, a sample mean is obtained and used as a point estimate for the true mean mu, or the number of hours the light bulb burns. Now let's assume, based on historical data, that the light bulbs are assumed to have a normal distribution with a known standard deviation of 65 hours. Then we would say that sigma is 65 hours. Now let's say this past week a sample of 50 bulbs was measured, and the sample mean that was obtained was an x bar of 1,045 hours. This sample mean of 1,045 hours provides a point estimate for the true population mean mu. What we would like to do is compute the margin of error for this estimate to obtain an interval estimate for the true population mean. Using what we learned previously about sampling and sampling distributions, we know that the sampling distribution of x bar follows a normal distribution with a standard error, sigma subscript x bar. And this is equal to sigma divided by the square root of little n. In this case, that would be 65 divided by the square root of 50, which is 9.19. This graph shows the sampling distribution of how the x bar values are distributed around the population mean mu. Now, using the standard normal probability table, also called the z-table, we can find the interval around the mean that contains 95% of the values. We do this first by graphing the area around the mean that contains 95% of the values. Here we can see a line splitting the distribution in half at the mean mu. Now we draw two lines above and below the mean such that 95% of the values are contained within that interval. Now, to look this area up in the z-table, we need to split 95%, or 0.95, in half, so that half of the 0.95, or 0.475, is below the mean, and the other half, 0.475, is above the mean. And since we know that the distribution is split by the mean with 50% of the values below and 50% of the values above, then the tail area below the mean is 0.025, and the tail area above the mean is also 0.025. Looking at the distribution now, we see all the parts add up to 1, or 100%. You can see that 0.475 plus 0.025 is 0.5. So we have 0.5 below the mean, and again 0.5 above the mean. And of course, 0.5 plus 0.5 is 1. So now with all the parts of the distribution marked off, we are ready to look up the z-score for the area under the table that is 95% of the values around the mean. Let's start with the upper z-score. Remember, this value represents the cumulative area under the curve to the left of this number. So we would look up in the table the area of 0.475 plus 0.475 plus 0.025, or 0.975 in the middle of the z-table. Here is the z-table with the positive numbers, so we would look for 0.975 in the middle of the table and find it here. Then we would look up and to the left to read off the z-value of 1.96. So going back to the distribution, we can mark off a z-value of 1.96 here. Now for the lower z-value, we would look up in the negative z-table the area to the left of negative z, and that is 0.025. So let's look that up in the negative z-table. And we find 0.025 in the middle of the table, and then looking up and to the left, we find the z-value for that area under the curve is negative 1.96. Going back to the distribution, we can mark that z-value right here. So now we have a distribution with the z-values marked for the area that contains 95% of the values around the true mean mu. What is left now is to convert these z-values back into x-values. Remember that to convert a z-value back to any x-value or x-bar value, we use this formula. X-bar is equal to mu plus and minus the standard deviation for the sampling distribution x-bar, where the standard deviation of the sampling distribution is sigma over the square root of little n. So the formula ends up looking like this. In the red box, x-bar is equal to mu, the population mean, plus and minus z, the value we look up in the z-table, times sigma over the square root of little n. Now let's plug in the numbers for our example, and we get x-bar is 1045 plus or minus 1.96 times sigma 65 divided by the square root of little n, which is 50. And that gives us 1045 plus and minus 18.01, and that gives us an x-bar of 1026.99 and 1063.01. This graph shows the sampling distribution of x-bar, where 95% of the x-bar values must be within plus or minus 1.96 standard deviations of the mean. We see from this that 95% of the x-bar values obtained using a sample size of n equal 50 will be between 1026.99 and 1063.01 hours. The general form of an interval estimate for the population mean is x-bar plus or minus some margin of error. This general formula translates into x-bar plus and minus z times sigma x-bar. Remember that sigma x-bar is equal to sigma over the square root of little n. This translates for our example into x-bar plus and minus 1.96 times 9.19. Remember, 9.19 was calculated by dividing 65 by the square root of 50, which is 9.19. So now we get x-bar, the sample mean, which is 1045, plus and minus 1801. And when we take 1045 and add 1801 and subtract 1801, we get this interval around the mean, 1026.99 and 1063.01, where 95% of the sample x-bars will be located. What we have just calculated is called an interval estimate, and it is important to understand the reason that this is called an interval estimate is that it provides an interval around the mean instead of just one point. When we took a sample size of n equal 50 and obtained a sample mean of 1045 hours, that sample mean could be used as a point estimate of the true mean. We stipulated that the true mean is 1050 hours so that we can understand how sample means can be used to estimate the true mean. In real life, of course, we don't know the value of the true mean, mu. Now, by adding and subtracting a margin of error, we have calculated an interval. So instead of just one number as a point estimate, we have a low number of 1026.99 and a high number of 1063.01, within which the true mean is likely to be. Now let's suppose we take another sample of 50 light bulbs, but this time we get a sample mean of 1040. Then the interval estimate for this sample would be 1040 plus and minus 18.01, or 1021.99 as the lower limit, and 1058.01 as the upper limit. Here is what that would look like on the distribution curve. We see that the true mean mu of 1050 is still contained within this interval, but the interval is shifted over to the left since the sample mean of 1040 is lower than the previous sample of 1045. We can keep doing this, taking samples of 50 light bulbs and getting sample mean after sample mean after sample mean, and 95% of the time we will get an interval that does include the true mean of 1050. We just saw that these two sample means, when we drew an interval around the sample means of 1045 and 1040, we got an interval that did include the true mean. This will happen 95% of the time, which means that 5% of the time we will get a sample mean that produces an interval estimate that does not include the true mean. This is called alpha. So alpha percent of the time we will get a sample mean that does not include the true mean. In this case, alpha is 5% or 0.05. Now let's see what happens when we take another sample of 50 light bulbs, but this time we get a poor representation of the population, and the sample produces a sample mean of 1030 hours. This will happen alpha percent of the time, or in this case, 5% of the time. 5% of the time we will take a bad sample that does not represent the true population, as is in this case with an X-bar or a sample mean of 1030 hours. Now let's see what happens when we calculate an interval around this sample mean. Does it include the true mean of 1050 hours? Well, let's see. We get 1030 plus and minus 18.01, which gives us an interval of 1011.99 and 1048.01. We can mark this off on the distribution to get a better idea of where this interval falls, and we can see clearly by looking at the interval that is colored in red that it does not include the true mean of 1050. So let's review what we just did. We took 3 different samples of 50 light bulbs and obtained 3 different sample means. The first sample mean was 1045 hours, the second sample mean was 1040 hours, and the third sample mean was quite low, only 1030 hours. Each of those sample means could be used by themselves as point estimators of the true mean. But to be more realistic in our use of sample data, we draw an interval around the sample mean and use that as an interval estimate for the true mean. This is done by adding and subtracting to the sample mean a margin of error to get the interval estimate. We did this here for all 3 sample means. The blue colored interval is for a sample mean of 1045, and we can see the interval does include the true mean mu. The green colored interval is for X bar 2, and it had a sample mean of 1040. It also included the true population mean of 1050. And finally, the red colored interval is for X bar 3, which was a sample mean of 1030. And we see that it does not include the true mean. We will get a bad sample that does not include the true mean alpha percent of the time, and in this case that is 0.05 or 5% of the time. What we have just done to calculate an interval around a sample mean is called a confidence interval. The interval we calculated used 0.95 or 95% interval, so it is called a 95% confidence interval. That means we are 95% confident that the true mean exists within our interval, since 95% of all intervals that are constructed using the sample mean plus and minus some error will contain the true population mean. This is represented by x bar plus and minus a margin of error, or x bar plus and minus z times sigma over the square root of n. When we use a z-value of 1.96, we get a 95% confidence interval. This value of 0.95 is called the confidence level, and the interval created is called a confidence interval. So the interval we obtained by taking the sample mean of 1045 plus and minus the 1.96 times 9.19 was an interval of between 1026.99 and 1063.01. This is a 95% confidence interval for the mean based on that particular sample. Another term that is used in statistics when discussing interval estimation is the level of significance. This is always 1 minus the confidence level. So for our example, alpha is 1 minus 0.95, since we constructed a 95% confidence interval. So alpha is 0.05. That is our level of significance, 0.05. That level of significance, the area outside of 0.95 that is within the confidence interval, is the area in the tails. Take a look at the distribution and you can see that 0.95 is the interval around the mean, half above and half below. This leaves us with two tails, one lower tail area and one upper tail area. These two areas contain alpha, the level of significance, which is 0.05. So since the areas are divided equally and 0.05 is in both of them together, we need to split alpha in half to get the area in each of the tails, which is 0.025. So now we can see the distribution is marked with an interval around the mean containing 0.95 or 95% of the values, and then 0.05 or 5% of the values in the tails, with 0.025 in the lower tail and 0.025 in the upper tail. A 95% confidence interval is a frequently used level of confidence, and it is a good idea to remember the number 1.96 as the z-value that is used instead of having to look it up in the z-table every time. Here is a table of the most frequently used confidence levels and their respective z-values. Keep this as a handy guide so you don't have to look the numbers up in the table every time you need them. The most commonly used confidence levels are 90%, 95%, and 99%. This table shows the alpha values for each of those levels of confidence. So for example, for a confidence level of 90% or 0.90, alpha would be 0.10, and alpha divided in half, remember we have to divide alpha in half between the two tails, the lower tail and the upper tail, so alpha divided in half would be 0.05. Let's see how we would look up 0.05 in the negative z-table and find the z-value is around here. As you can see, there is no exact value for 0.05. We have 0.0495 and we have 0.0505. So 0.05 would be smack in the middle of these two. So looking to the left, we see the value is negative 1.6. And looking up, we see the hundredths value is between 0.04 and 0.05. So our z-score would be negative 1.645. Let's take another look at the table of most commonly used confidence intervals. We just saw how the z-value for a 90% confidence interval is 1.645. And previously, we found a 95% confidence interval had a z-value of 1.96. Now let's repeat this process with a 99% confidence interval. If we want to obtain a 99% confidence interval, then what would alpha be? We know that alpha is 1 minus the level of confidence, so 1 minus 99 is 0.01. And since there are two tails in the distribution, an upper tail and a lower tail, when we are constructing intervals, we always split alpha in half. So alpha divided in half gives us 0.005. Before we look this up in the z-table, let's try to visualize this. Here you can see a distribution that has a 99% confidence interval marked off around the mean. Knowing that the entire distribution is equal to 100%, and we have 0.99 marked off in this interval, then 1 minus the confidence level, or 1 minus 0.99, is equal to 0.01. Now alpha is the area in both tails, and since we have two tails, a lower tail and an upper tail, then we must split the alpha area of 0.01 between these two tails, and we get 0.005 in one tail and 0.005 in the other tail. That's alpha divided in half. Now when we look at the distribution, we see it adds up to 1, with 0.005 in each tail and 0.99 in the middle. Now that we understand that, we are ready to look up 0.005, the lower tail area, in the z-table. The number we should get is here, 2.576. Okay, back to the z-table. We look for 0.005 in the middle of the table, and the closest number we find are two numbers, 0.0049 and 0.0051. And of course, 0.005 is right in the middle of these two. So looking to the left, we get negative 2.5, and looking up to the hundredths value, we get somewhere between 0.07 and 0.08. So the z-value, according to this table, is minus 2.575, right between minus 2.57 and minus 2.58. We see in this convenient table the z-value is marked off as 2.576, not 2.575 when we use the z-table. The reason for this discrepancy is that this value, 2.576, is actually more accurate when you look at more than 4 decimal places. The z-table only goes to 4 decimal places, so we get 2.575. But if you were to use Excel or calculate using calculus, you would get 2.576. Consider this a rounding error. Many textbooks simply round this number up to the nearest hundredths place and use 2.58. For our purposes, we will continue to use either 2.576 or 2.575 whenever we use a 99% confidence interval. Just to make sure how to draw a confidence interval when sigma is known, let's take a look at one more example. Let's say we want to draw a 90% confidence interval estimate of the population mean grades on a departmental statistics exam. From historical data, the population standard deviation is known to be 15 points. Suppose a sample of 75 students are taken and the sample mean is 70. The distribution for a 90% confidence interval would look like this. You don't have to draw this interval each and every time you construct a confidence interval, but it is helpful in visualizing the data and to understand what we are doing. Since our confidence level is 0.90, then the level of significance alpha is 0.10, and alpha divided in half would be 0.05. This number is what we would look up in the z-table, and since we have done this before, I won't repeat the process here. If you recall, the z-value for 90% confidence was 1.645. You can rewind and review how we got that a couple slides back. Let me point out the notation I use here. If you'll notice, I didn't just write z this time. I wrote z and then subscript alpha divided in half. This is a more accurate and precise notation of the z-value when alpha is split in half. Here I have marked off the z-values on the distribution curve. Now it's time to plug this into our formula to get a 90% confidence interval around the true mean. If you recall, the formula is x bar plus and minus a margin of error, which is x bar plus and minus z times sigma over the square root of n. Now all that is left to do is to plug in the numbers and calculate the interval. So we get 70 plus and minus 1.645 times 15 over the square root of n, which is 75. And so we get 70 plus or minus 2.58, I rounded it to the hundredths place for convenience, and 70 plus or minus 2.58 gives us a lower limit of 67.15 and an upper limit of 72.85. This means we are 90% confident that the true mean is between 67.15 and 72.85 based on this sample data. That concludes this video tutorial on interval estimation for sigma known. Please be sure to watch the next tutorial on confidence interval estimation for sigma unknown. I hope you enjoyed this tutorial and I hope you learned something.